Good morning, everyone. I'm Sina. I'm one of the PhD students in HyFiSyn project from KU Leuven. So today I'm going to talk about the interface between fiber and matrix in basic terms as possible. So I will address these questions in my presentation. So the first one is, what is the fiber-matrix interface? What is the definition behind it? And what are the main historical models that are presented in the literature? And how does the stress look like in a fiber when there is interfacial failure happening? And what are the possible characterization micromechanical methods that you can use to characterize the interface? So I will quickly start about this material science tetrahedron. So the structure dictates the properties, but the structure and properties are not independent. So they depend also on other concepts such as performance and processing. And at the core of this tetrahedron, there is some problem. It happens here, but I don't see it there.
Which slides in now? This one. Maybe you can skip this slide. Yeah.
Okay, so these were the 4 questions that we needed to address in this presentation. So as I said, in the core of this tetrahedron is the characterization and the modeling and the experiment, which is also the core of this presentation today. So, okay, as you know, the properties of a composite is determined by 3 components: fiber, matrix, and of course the interface. So in the literature, the interface is regarded as the heart of the composite. Why is that? Because the interface has this vital duty to transfer the stress from matrix to the fiber. And you would ask which global properties are affected by these interfacial properties. So among many, it is fracture strength, stiffness, fracture toughness, transverse strength, the failure mode of the composite, and also its response to the environment. But why do we care about this interfacial failure in composites? Well, if we are looking at the bigger picture, we are interested to see that how the stress will redistribute itself in the broken fiber in a full composite. And more importantly is that how the stress will redistribute on the neighboring intact fibers. So we don't want to overestimate or underestimate the failure strain of the composite by correctly representing and modeling the interfacial failure. So we will answer this question that how an interface is formed in fiber reinforced polymers. So there are 6 main ways that the interface can form. The first one is the molecular entanglement, and then there is interdiffusion of the elements. And also we can have an electrostatic attraction between fiber and matrix. Or we might have also the chemical reaction between these functional groups on the fiber and matrix surface. We can have either a chemical reaction forming a new compound on the interface, or we can have this mechanical interlocking. So as you know, there is this huge mismatch between the elastic modulus of fiber and the matrix. So if we imagine a short fiber embedded in a matrix, and if we apply stress to both ends and strain it, we will see that something is happening. We can see that there is a larger shear deformation in the fiber ends. And if we use the force balance, we will end up with this equation. I don't want to go into details, but bear in mind that we can solve this equation for the stress in the fiber. But what is the physical meaning of this equation? Well, it means that the longitudinal stress in the fiber, shown by sigma sub f, builds up on the, in the fiber through the accumulation of the shear stress, interfacial shear stress. So we have to find the relation between the shear stress as a function of x, which is the distance along the fiber, in order to be able to solve this equation. So I will take you down the memory lane to 1964 into University of Cambridge, where Cottrell, independently, but at the same time with Kelly and Tyson, were working on the same topic. So what did they assume? They assumed that the matrix is perfectly plastic, meaning that the interfacial shear stress is constant, and it equals to the shear yield strength of the matrix. By considering a simple representative volume element, they will be able to solve this equation by simply considering tau as a function of x as a constant. So this means that the stress profile in the fiber will be symmetric about the center of the fiber. And also we expect the maxima from both ends in the center of the fiber, meaning that the maximum stress in the fiber is a function of the fiber length. So imagine that there is a critical length. If we are below this critical length, the stress profile shown by a red color in the fiber, and also the interfacial shear stress shown by the green color, will look like something like this. But if we are exactly at this critical length, it will look the same, but the maximum stress will be higher. And if we are beyond this critical length, we will also end up having a plateau in the stress profile. So this parameter called critical length is really important to consider in the interfacial characterization, mainly in stress-based methods that you're going to see further in the presentation. It's gone.
But it's to connect with them.
Okay, thank you. So in the previous slide, we talked about this critical length that is really important, and also the Cottrell-Kelly-Tyson model overview. So another building block of the today's modern numerical models or the analytical models is another model called a Cox model, where he assumed that both fiber and matrix are fully elastic, and he assumed that there is a perfect bonding between the fiber and the matrix. So no debonding was allowed. So we conclude that it is somewhat more realistic than the Cottrell-Kelly-Tyson model. As you can see in the Cottrell-Kelly-Tyson model, the interfacial shear stress was a constant, but here you can see its relation with the shear rate. If we compare both models, we can see the differences in how it looks, that if we are plotting the stress in the fiber along the length of the fiber. There is another model, which is called the partial bonding model, which is assumed to be more realistic than all of these. And it physically also makes sense. If you have a broken fiber and then it starts to debonding, you will assume that there should be an interfacial friction taking place at the end of the fiber where it is debonding occurred. So we can see that this initial linear stress buildup in the broken fiber. And as we go further, we recover the stress and then we reach the plateau. You can also see the comparison between the Cox model and also partial bonding model. But you would ask, am I sure about it? Like if it is more realistic one?
Yeah, sorry.
We will know in a minute.
Yeah, there's an issue with screen share. It was not working on Zoom.
You exhausted the system.
Yeah, apparently. Now it should be okay.
Yeah.
Okay. So here again, you see the
That's on the PowerPoint.
okay, so we had this initial linear stress recovery part of it, which is representing the debond length also. And then, yeah, I asked you, you would ask me, am I sure about this? So I will take you to early 80s, where micro-Raman spectroscopy was developed and used in the fibers for the first time. This method can distinguish between the bonded and debonded phases of a carbon epoxy. And you can use this model to validate your stress transfer model. So what is the principle behind this method is that.
Sorry, it's still not working, I think.
Okay.
Now it's working.
Okay, the principle behind this laser Raman spectroscopy method is that it evaluates the vibrational frequencies of the excited fiber by a laser light. So if we do some experiments with using a laser Raman spectroscopy, we get this orange point, as you can see here. And this is the Cox model that is tried to be fitted to the experimental data. You can only see that in the plateau, it reaches to the points. But you can see that how perfectly a partial debonding model can represent the true interfacial behavior of interfacial failure. Okay, so far I was talking about how does stress looks like in the fiber, but let's look at how stress looks like in the interface, basically interfacial shear stress. So this was how interfacial shear stress looks like with the Cottrell-Kelly-Tyson model. And this is how it looks like with the Cox model. And this is another model in the literature. You can see how it differs from there, that the shear stress reaches 0 on both ends of the fiber. And this is more accurate model, the partial bonding or the partial debonding model.
Yeah, now you should be good to go. Hope you have glasses.
Okay, so we compared the energy-based and stress-based analysis in interfacial failure. There is another important model in the literature where you relate the traction and separation on the crack faces by using a bilinear relation. So what is the meaning of this? You basically load your carbon on fiber, and the interface is applied with the cohesive zone model. When you reach the interfacial shear strength, the softening begins, and the area under it is representing the fracture toughness that you are put it in your model. But if you remember, in the partial debonding model, there is also a frictional region. So in order to take care of that, you also need to define a friction law. Simply, you can use the Coulomb friction law. And if you combine this, you can come up with an interface model that you can implement in your finite element model. So in this case, you will end up having a stress-based initiation, but your debond propagation will be energy-based, and you will also take care of the frictional behavior. But if you are going to use this, don't forget to take care of these other things that are happening in interfacial failure, which are the matrix plastic behavior should be included. And you could also consider the matrix crack, and also the thermal residual stresses should also be taken care of. Okay, I will first start with the first micromechanical test that you can do to get the interfacial properties. This is called single fiber fragmentation test, where basically you embed a fiber in center of a dog bone shaded specimen or a straight specimen. And it is among the 4 tests that I'm going to introduce to you, is the only test that involves the breaking of a fiber. So you strain it, and then you end up with having few fragments, you strain it more, and then you end up having more fragments. But at some point, you reach this stage that there is no new fragments are developing. So it is called the saturation level. And in order to meet this saturation level, as you can imagine, the matrix should have a higher failure to strain than the embedded fiber. So if you remember, I also briefly talked about the critical length. So with this test, you can get the critical length, but there are different approaches. So if you reach the saturation level, you end up having a few fragments. You can basically get the average of it and consider it as a critical length, or you can most commonly use the 4/3 of the average length, or you can consider the maximum fragment you see from the microscopy as your critical length. Let's see how it looks like under microscope and cross polarizers. So the debond zones can be observed using the photoelastic birefringence. So you see a carbon fiber here with the epoxy, and you can see the debond zone. And the birefringence shows that the stress state near the fiber breaks and the interface. So basically we strain it more, and you can see this pattern is flattening down. And we can see that also there are 2 distinct colors near the fiber break, representing the inner and outer zone. And as you go further in the strain, you can see this distinction clearly. But I would also say that upon unloading, the outer zone will disappear and only the inner zone will remain. So to make it more clear, imagine that we have a fiber, and then the fiber break happens, and there is no debonding yet, but you can see the pattern, how it does look like. And then you apply load more, and you end up having a debonding, where you can clearly see 2 different zones. But if you remove the loading, you will end up with just 1 zone. So there are different approaches to consider which one as a debond length in the literature also. So what are the advantages of single fiber fragmentation test? It is a better replication of in situ events that happens in a real composite, because basically you have fiber break, and the fiber is fully embedded in a matrix. And it is also good for characterizing the interface of brittle fibers, such as carbon fiber. And with a single fiber, with a single test, you can yield a lot of data. But the limitation is that the strain to failure of the matrix at least should be 3 times higher than the fiber. And in order to be able to do microscopy on it, the matrix should be also transparent enough. But it is a time-consuming test, because basically you have to check in every strain increment how many fragments you have, and you have to probe over the whole length of the fiber from the whole length of the specimen. The second test I'm going to introduce is the single fiber pull-out test, where basically you have a droplet shape of a matrix, and you embed a fiber, and you cure it, and you pull the fiber out of it. And in order to have the pull-out happening, the fiber embedded length must be less than the critical length. Otherwise, you will end up with having a fiber breakage. This is the embedded length, which is embedded in the matrix droplet. And you can do the data reduction by simply assuming that there is a uniform interfacial shear stress, which is not a good assumption, but it is easy to do. So basically, you do some few tests, and you get the maximum force on the load displacement, and you plot it against the embedded area, and the slope will give you the interfacial shear strength. What are the advantages? It is a direct and easy way to measure the interfacial shear strength. And it's relatively easy to do compared to the single fiber fragmentation test and straightforward data analysis. And it is an excellent method for novel fibers, matrix systems, such as these fibers with interfacial topographical anchors. But there are some limitations to it. It is governed by the critical length, so you should be careful of the free fiber length and also the embedded length. And the maximum embedded length, because it's too short, is tens of micrometers, so it is really hard to handle. And it will be a little bit challenging for brittle fiber systems. The third test is the Microbond test, where you basically form a droplet onto a surface of a fiber. And you can either pull the fiber itself, or you can load it by using the loading blades or the fixed knife edges. It is similar to the pull-out test. And the things that you should be careful about is the position of these blades. You don't want them to be too narrow or too wide. And also, if you're going to use analytical models or the finite element models, you should also take care of the geometry of the droplet. You should consider it the way it was on the test. And also, yeah. So let's look at how the load displacement looks like. So we have 4 stages mainly. The first one is the elastic behavior here, and then you increase the load more, and then you will end up with a slope change or a few load drops, small, tiny load drops, where the interfacial debonding can be assumed. And then at the third level, after the maximum load, you will end up with residual friction forces, and after that, there will be a complete debonding. So the advantages, there are more studies on it recently, and you can find some recent developments that fully automates even the sample preparation and also the testing of it. So it could be easy to do. And it can be used for any fibre-matrix systems, but some limitations. Again, limitation on the droplet size due to this critical length. And it would be challenging since we want the shear debonding rather than the droplet slippage or the fiber breakage, so that your success rate will be lower. The last test is the push-in or the push-out test, where you basically take a small sample of a full composite, the bulk composite, and you polish it, and you put it on a specimen holder. So a specimen holder can be fully closed or slightly open, depending on the type of the test, and you indent it with an indenter. This is suitable for the fibers that can carry compressive stresses, such as carbon fiber, but it's not good for the aramid fibers at all. So again, similarly, the load displacement, we start with elastic behavior, then interfacial debonding occurs, and the fiber will be pushed through, and then after full debonding, it will have an interfacial sliding, and at the end, slightly rise because of the closure of the indenter with the matrix. And you should be careful that you select the fibers that you are going to test on your sample or the membrane that are selected randomly. And the differences between push-in and push-out is that the push-in test requires the polishing of one surface. However, the push-out involves the fabricating a thin membrane, which is around 50 micrometer, or sometimes in the literature as said as the 3 to 5 times of the diameter of the fiber, which is really thin. And things to consider is that the indenter tip geometry plays a big role, and how you also place it on top of the fiber that you are going to push. And we can avoid the splitting or rupture of the fibers, for example, by changing the indenter tip to a more proper one. And also, one of the things to consider that the indented tip with a larger radius of curvature than a fiber radius are advised against. So it should be really comparatively to the radius of the fiber. Okay, so from all these tests, we can get interfacial properties. But if you go through the literature, you can see that there is a large variation in the reported interfacial shear strength, interfacial fracture toughness, and also the friction. So if you have a quick look at the reported data from the literature, you can see and compare that there is a big variation in the interfacial shear strength, fracture toughness, and also the friction coefficient for the same kind of material throughout the literature. And there is still ongoing debate based on these reported properties that which method is the best. We simply don't know, but we should be hopeful that these tests are shedding light on how we see the interfacial failure, and we can have our knowledge deepened based on what we see in the test, that how will the composite fail as one of the mechanisms to fail a composite by interfacial failure. I will also mention some honorable mentions, which are not that popular compared to the previous 4 tests. We have a 3-fiber test where we have a 2 horizontal fiber, 1 vertical where you pull, and there is some resin that attaching these 3 fibers. We also have single fiber Broadband test where you do this compression on a double notched specimen. We also have, instead of a single fiber pullout, we have also a fiber bundle pullout. And we also have single fiber peel test, where basically you have a capsule filled with resin and you gently put a fiber, single fiber on top of it, but you make sure that at least 50% of the depth of the fiber is embedded on top of it. And then you peel, basically you peel the single fiber. So conclusions. By far, we know that there are imperfections in the test, in the data reduction schemes. And also there is a big variation of the data that acquired on the same material system between the labs, different labs in the world. And we should also consider that what we see in this single fiber micromechanical tests are somehow different what will happen in the real composite. And these tests are highly stochastic in nature. So the more tests you do, the better results and better idea you will have about your material system. But what can we do further as a future work? Well, we should come up with standards for these tests. And to do so, one of the means to do so is that we should do more round-robin exercises where a similar material is distributed between different labs. And at the end, the data acquired are compared with each other. And we can also incorporate these advanced new tools such as digital volume correlation or 4-dimensional in situ synchrotron radiation computed tomography. And we can see that what is really happening and are we satisfied with our data reduction skills. So with that, I conclude my presentation. Thank you for listening.